This is an extended version of the talk presented at the Scale by the Bay conference yesterday. What is Chymyst? It is a Scala implementation of the chemical machine paradigm of concurrency, which is also known as joint calculus in the academic world. The chemical machine paradigm was invented about 20 years ago in this paper. I do not suggest that you start by reading this paper. I will explain the chemical machine paradigm in this talk. Joint calculus is not actually a mathematical calculus, it is a programming language, just like lambda calculus is a programming language. Joint calculus, or the chemical machine as I prefer to call it, is a declarative language, which is a domain-specific language for concurrent and parallel computations. It is largely unused and unknown by the software practitioners. I made a new implementation of it available as an open source Scala library and embedded domain-specific language. The problem with concurrent and parallel programming is that the usual tools, such as threads or semaphores and so on, force us to focus on reasoning about mutable state, reasoning about states that mutate in parallel in different processes that run at once. It's very hard to reason about those things. It's very hard to write a program that mutates a state from several different processes without errors. Also, these programs are very hard to test. Every time you run them, they give you a different result. The runtime behavior is non-deterministic. This is known as a race condition. There are also other problems such as deadlocks, which is that several processes wait for each other, but neither one can make any progress because they're waiting for something that never happens. Or a live lock, where several processes are busy doing things, but actually nothing gets accomplished. Things are repeated over and over because of an error in logic about which process has to start what at what time. It's very hard to reason about such things. So programmers usually avoid having to face these problems, and they use declarative approaches to concurrency. Some of these approaches are synchronous parallelism, such as Spark, or parallel collections, asynchronous parallelism, such as futures or async await constructions, streaming systems, actor systems, and a chemical machine is another one of such approaches. A typical example of a concurrency problem is dining philosophers. You see the dining philosophers problem. Read this page if you're not familiar with it. The problem is to simulate this process while avoiding deadlock and starvation of philosophers. Rosetta Code is this website that gathers various programs solving the same problem in different languages, in different programming languages. So this page shows solutions for the dining philosophers problem in different programming languages, such as C, C++, C#, F, and so on. So let's look, for example, at the C# solution. The program is quite long. It's not obvious what it's doing. There are lots of declarations and logic that's not obvious. Obviously, there are some states it's trying to get forks or currently holding left fork, try to get and so on. So this is an imperative logic that's quite hard to follow. It's not clear what's happening. These are probably concurrently running processes. So that's what I was talking about when I said it's difficult to reason about it. If there's an error in this program, how would we find out? That's quite difficult. In this talk, I will introduce the paradigm called joint calculus, which I prefer to call the chemical machine paradigm. I will show you code using Chymyst, which is my open source project, implementing this paradigm in Scala. I will also show how joint calculus, or chemical machine, can be viewed as an evolution of the actor model, or an improvement upon the actor model. I'll give you some examples. I will not mention in this talk approaches such as pi calculus or CSP, which is communicating sequential processes, which is the basis of concurrency for the Go language. I also software transactional memory is available in Haskell and Scala as another concurrency paradigm. So these are alternatives. I believe that the chemical machine is superior to all of them. The chemical machine does not use threads, semaphores, locks, or shared mutable state. You can think about it as an improvement upon the actor model, where the main difference is that actors are automatically started. In the usual actor model, you need to create each actor and initialize it maybe with its state, monitor its life, restart it when it died, and so on. In the chemical machine, imagine you still send messages to processes, but you don't have to start those processes yourself or monitor them or hold references to them. It's as if actors were automatically started for you. Whenever you need them, just send messages. They will be started when necessary. Also, actors need to be type safe and support multiple dispatch, meaning that an actor can wait on several messages at once, and the message can be sent to several actors who would be then waiting for it. In the chemical machine paradigm, concurrency is automatic, parallelism is data-driven, not command-driven. I will show exactly how that works. It makes it much easier to reason about. Any other concurrency formalism I know is harder to reason about. However, this is a new paradigm. You need to understand it and learn how to think about concurrency in the chemical machine paradigm. I find two metaphors helpful for learning about the joint calculus or chemical machine paradigm. One metaphor is that it is about concurrent functions that compute with concurrent data. And the other metaphor is a chemical soup with molecules and reactions. I will now explore both of these metaphors and show you that they are equivalent. So as I said, actors that are automatically started mean that you just send a message and some function is automatically called on the data that this message carries. So this is the same as saying we have a concurrent function call on some data item. What does it mean if we make functions concurrent? We want to stay within the functional programming paradigm. So clearly, several functions should be able to run at once. That's what we want. And also, functions should not have any shared state. so that concurrent instances of functions should work on different data items, not sharing any data items or state. This will be implemented if we label each data item for consumption by specific concurrent functions. So in some way we need to label that, otherwise it's not clear which function needs to be called if I create a data item, say, with integer value 100, unless this 100 is labeled in some way so that concurrent functions can be called correctly on this 100. So clearly we need to store all these data items and functions in some special site where data items wait for functions to be called on them. And then concurrent functions will consume data from this site, compute some results, and emit them back to the site. This is how it will work. Whenever input data is available at the site, then concurrent functions will automatically start and begin their computations. And then different instances of a concurrent function can consume different separate data items from the site. So right now this is a little nebulous and lacks a specific implementation detail, but this is the intuition behind how to make functions concurrent and how to make actors automatically started. I prefer this second metaphor, which is the chemical metaphor. So now let me talk about that. Consider a chemical equation, chemical reaction. Chemists write reactions in this kind of syntax. For example, a molecule of hydrochloric acid reacts with a molecule of sodium hydroxide, and both of these molecules disappear. Instead, the molecule of salt and the molecule of water appear. Now, instead of real chemistry, we're going to use abstract chemistry, which means that we arbitrarily define molecules, not necessarily corresponding to any real chemistry. So we imagine a chemical soup that can contain multiple instances of these abstract molecules, let's say molecules A, B, and C. And then we also declare the chemical laws or reactions. For example, that A plus B react and yield the molecule A, and A plus C react and yield nothing. Note that in real-life chemistry this is impossible. You cannot have two molecules reacting such that one of them just disappears. But this is not real chemistry, so we are free to define any laws we need or we want for a particular application. This diagram illustrates the reaction. So A plus B are going to A, so it means A and B are consumed and A is emitted. A plus C going to nothing means that A and C are consumed and nothing is emitted. So the program code can define that there exist molecules A, B, C, and so on, and specific chemical laws. And at the initial time, the code will emit some initial molecules into the soup, as it were. The runtime system will be implemented that will look at what molecules are present. For example, let's say 10 A's and 5 B's and 6 C's and so on. The runtime system will decide which reactions can take place, run these reactions, emit the product molecules back into the soup, and again examine the soup to see if any more reactions can take place, and so on. Note that in real chemistry, each pair of molecules reacts independently of each other pair of molecules. So all reactions proceed concurrently and in parallel. We want to follow the same scheme. We want to follow this metaphor of chemistry so that all of these reactions will be simulated by the runtime system concurrently and in parallel, as long as the input molecules are available. Now, suppose that we implemented this simulator, the chemical machine simulator. We would like to use it for actual computations, not just to watch reactions happen. To do that, we add data to this model. So now we say each molecule must carry a value of some type, let's say integer value or string value or some other value. So this will be the concurrent data, the molecule carrying a value. Now imagine we made that change to the reactions shown in the previous slide. Means that we now have molecules A carrying value X, molecule B carrying value Y, and the reaction should emit molecule A carrying some value Z. So clearly the reaction needs to compute the Z, otherwise you cannot emit the molecule A, right? All molecules must have a value on them. So naturally, it follows that a reaction should run some computation, should evaluate some expression so that Z can be computed, and X and Y can be used naturally as inputs to that computation. So reaction carries a function that computes Z given X and Y. So here's a code example in the Chymyst syntax. I will show more of this and explain more of this later, but you can see that the syntax is very close to the chemistry notation. A of x plus b of y goes to a of z, and z is computed as some function of x and y. In the second reaction, let's suppose that C carries an empty value, which is modeled in Scala as the unit value. A still carries this x value, let's say it's integer or whatever. Then this reaction doesn't emit any molecules, but it could perform a side effect, such as printing. We could write arbitrary Scala code in this reaction body. So, to summarize, we just added the requirement that each molecule carries a value, and it naturally follows that reactions must carry functions. Each reaction can also emit molecules, so we can think about it as a molecule set valued expression, but it doesn't have to be thought of that way. We can actually write arbitrary Scala code emitting molecules or performing side effects. The resulting molecules, if emitted, will be put back into the soup, and we'll be able to react again with further molecules. As we said, the runtime system must be implemented in such a way that it will start reactions concurrently and in parallel whenever sufficiently many input molecules are available. So the operational semantics is that when a reaction starts, all the input molecules for that reaction instantaneously disappear. That's an atomic action, so they disappear both at once. So in other words, the runtime system examines what molecules are present in the soup at this time. It finds some instance of A and some instance of B. There could be many. It just finds non-deterministically any instance of A and any instance of B. These two molecules are instantaneously removed from the soup. The values on them are substituted into the body of the reaction. The body is then run, asynchronously and in parallel with any other such reaction body. And when the body of the reaction specifies that the molecule needs to be emitted, then this molecule is put back into the soup. So another instance of A carrying a value Z is created and returned to the soup. This is how the chemical machine simulates reactions and in this way performs arbitrary computations. So this is actually the entire model. There is nothing else in principle to learn about the chemical machine to be able to implement it. What remains for us to learn is how to use this paradigm for implementing actual concurrent computations. So for example, consider the task of implementing a concurrent counter. So the counter holds an integer value, and we should be able to increment or decrement this integer value concurrently. That is, many different processes should be able to send increment or decrement requests concurrently, and this should not lead to mistakes. Now, if you think about implementing this without the chemical machine, then there might be a race condition unless you take care about this operation. One process could start incrementing, another process could also start incrementing, and they could interfere with each other. How do we do this in the chemical machine? Well, the only way to make any computation happen in the chemical machine is to define molecules and reactions. So what molecules and reactions should we define? That's the first question while implementing any computation in the chemical machine. In this case, it is clear that the integer value of the counter must be carried by a molecule. Let's call this molecule counter. We're free to define molecules with any names, so let's just make it easier to understand for us. We choose the name counter. The decr and incr are molecules that will be used to signal a request to decrement or increment. So whenever some process needs to increment or to decrement the counter, the process will have to emit one of these molecules into the soup. Then we define two chemical reactions or laws. The first one is that the counter molecule and the decrement molecule react and emit a new counter molecule, and the value that this new counter molecule will carry will be equal to this value minus 1. So this is a very simple reaction body, but this is a computation. So we take the value that the input molecule carries, perform a computation with that value, and put a new value on the new molecule that is emitted back into the soup. That is how the chemical machine performs computations. The second reaction is similar. It increments the counter value. The code should initially emit a molecule counter into the soup. So let's say initially we emit counter with value 0. And then other processes could emit decrement and increment molecules at will at any time concurrently. How would that work? Suppose that we have a counter molecule with value 0, and then some processes emit 5 molecules with decrement, so 5 decrement molecules. The chemical machine will examine the state of the soup and find that the soup contains 5 decrement molecules and 1 counter molecule. Then the chemical machine also will examine the chemical laws that are declared, and there are these laws, so one of the counter and decrement pairs can react. But actually there's only one copy of the counter molecule and several copies of the decrement molecule. So the chemical machine runtime must choose one of the decrement molecules that will react with this single instance of the counter molecule. This choice is non-deterministic in general. Then the chemical machine will remove both molecules from the soup. At this point, the soup will contain maybe several decrement molecules still, but no counter molecule anymore. So while this computation is performed, the counter molecule is gone from the soup. So this prevents any other reaction from running, because all reactions require a counter molecule as an input. So while the counter molecule is absent, it's completely safe to perform this computation and then emit a new instance of the counter molecule back into the soup. When that is done, another reaction can start. So it is clear that there cannot be any mistake, and two reactions cannot run at the same time, trying to increment and decrement this value, obtaining incorrect results. Here is how this program is written in the syntax of Chymyst. First, we define the functions that will emit molecules into the soup. These functions are called molecule emitters, and they define at the same time the sort of molecules that are available. So the sorts, the chemical identities of the molecules. We define three molecules: counter, decker, and incur. This M is the function that the Chymyst library defines. And we specify the type of the value that the molecule will carry. Then we declare reactions, such as this. The go is the function that the Chymyst library provides, and then the argument must be a partial function with a single case clause. The left-hand side of the case expression is a pattern match on the molecule values. The right-hand side is arbitrary Scala code that can use these pattern variables. In this case, it's a very simple pattern. We match on any value n that the counter carries, and the decrement molecule has unit values, so we just match on underscore. We could match on the unit value directly as well. It's the same. Having defined these reactions, we have not actually started anything. So these are values. These are values of type reaction, and they are declarative. They do not actually start any processes when you say val r0 equals go. This declares a chemical law, but it does not yet start anything. And at this point, you're not allowed to emit any molecules yet because you have not activated any reactions yet. This is the call site, which is again, site is a function provided by the Chymyst library. This call activates the two reactions. After you do that, a reaction site is created, which stores these reactions, and it will also store the molecules when you emit them. So after saying site, you're allowed to emit these molecules, and they will go to their site. Once the molecule is at the reaction site, it's waiting for a reaction to start. But all of this is implicit. Your code does not contain any of this waiting or scheduling. It's all automatic. All you do is emit molecules, declare reactions, and activate them. You can also declare reactions inline, which is to say you can just put this code directly here into the site call. This is so because these are just values. These are immutable values. They do not have side effects. So you can declare them inline, or you can first declare a bunch of these reaction values and then activate all of them together in a new reaction site. Having done this, we can start emitting some molecules, for example, increment, increment, and so on. Now, calling this emitter immediately returns unit. It's a non-blocking call, which is very quick. It emits a molecule counter with value 10 as a side effect into the soup. These are also non-blocking calls to the emitter that emit copies of the molecule into the soup. They return very quickly. So initial state of the soup after this would be that, and then reactions will start. Incur and counter 10 will react and give you counter 11, and then another incur that's still there will react with counter 11 and give you counter 12 a little later. Let us see how we can do this. I will use the ammonite REPL. So I'm going to import the Chymyst library. And I'm going to type in this code, and we'll see how it runs and how we could probably debug it as necessary. So I need this import statement. Then I say val counter equals m int, and that defines a new molecule and a molecule emitter at the same time. Let me just do decrement, and I'm going to define reaction right away in the site call. So I define the site. There are no warnings or errors. The site call returns a warnings and errors structure right now, which you could examine. It would have printed the warning if there are any. So now I can say counter 10, let's say. You see, it returns unit, so it's a side effect. Now I say counter log soup. So this is a debugging function. Yeah, it's a function without arguments. It returns a string which says there are a molecule counter with value 10. Ignore the /p for now. This is just another feature I'm not going to use right now. So now let's emit some Decr molecule. And then again log soup. You see the counter has now value 6, which makes sense. So that is how it works. These are asynchronous calls. What if I did Decr and counter log soup at the same time? Then you see the soup still contained 2 molecules when the log soup was called. But if I do log soup now, then it will be 5. So in this way you see that these are asynchronous calls that are executed on a background thread concurrently with your code that emits the molecules. So this chemical metaphor is equivalent to the concurrent data, concurrent functions metaphor. When in the chemical metaphor a reaction consumes molecules, that is similar to a concurrent function consuming its input values, which is each of the input values is an item of concurrent data. So molecules are this concurrent data. When the reaction emits a molecule as a result, this is similar to functions that return result values. When you emit a molecule with a value, it's equivalent to lifting data into the concurrent world. When you define a reaction, that's equivalent to lifting a function into the concurrent world. And the reaction site is that container for concurrent functions and data items that is necessary for this to work. Before I show you more working code, we need to learn about another feature of Chymyst, which is called blocking molecules. The molecules we have seen until now, these ones, are non-blocking. There are also molecules called blocking. The difference is that when you call an emitter for a blocking molecule, the emitter will block your execution until the reaction starts consuming that molecule. The emitter call will block also until the reaction replies to the caller. So there is this concept of reply value, which I will illustrate right now. The blocking molecule implicitly carries an emitter for the reply. And when it's called, then the value is magically returned to the caller of the blocking emitter. So here's an example. Suppose we define a blocking emitter like this. Note that there's this B function, which is defined by the Chymyst library. It has two type parameters. The first type parameter is the type of the value that the molecule carries. And the second type parameter is the type of the value that the reply will carry. So this reply is not actually itself a new molecule that you define, but the emitter for the reply is available within the reaction body. It's only available within the reaction body. So here's how you use it. You emit the molecule with an integer value, just like a normal molecule, like you emit this molecule, which is non-blocking. But while this call is going to return immediately with a unit value, this call will block until this reaction can start. Now, this reaction says molecule F reacts with molecule C. So unless the molecule C is present, this reaction cannot start. So if we did not emit the C here, this call would block until some process emits a C molecule. Now, in this example, we first emit the C molecule and then we call this. So when we call this emitter, when we emit the molecule F into the soup, the C molecule is already there, so the reaction can start. And the reaction body says to call the reply with this value. Now, the reply is this implicit emitter, this magical emitter that you did not declare. You see, you only declared this B and the type of this emitter. You did not actually declare the emitter reply, but it is available in this pattern matching. Let me implement this and show you how that works. So I will also define now the molecule C, which is going to be non-blocking. Note, I cannot use the molecule counter. The molecule counter is already defined in the previous reaction site, and reaction sites are immutable. I cannot add new reactions now anymore. I should have defined all reactions back there in the reaction site. You see how that works. If I say site go case f of n reply. Now see, f must have two pattern variables in the case expression because f is a blocking molecule, so n will have type int, reply will have type a function from string to something, to boolean, I think. But let's look at this. So here's how I define this. So n is an f, then I have, let's say I have m on the molecule C, and then I do, for example, I can say val result equals, I can do whatever I want, arbitrary Scala code here. Let me just make it simple. Result equals n plus m, and then I emit reply with result. Now close the go, close the site. All right, no warnings or errors. So now let me emit C of 100, and now I emit F of 200. And the result is a string, which is result equals 300. So the call to F returns a string. It's like a function. It's a blocking call, just like a function call, that returns a value. It's very convenient to have this functionality. But of course, most of your code should be non-blocking, and you can organize your code this way very easily. What would have happened if I wanted to now use this F with the molecule counter that we defined just before in this session? There's an error. Exception that molecule is already bound. Molecule counter cannot be used as input since it is already bound to that site. So you see this error message tells you that this reaction site that I'm trying to define here cannot be defined because there's another reaction site that already binds the molecule counter. Molecules can only get bound to a single reaction site. Otherwise, it would make no sense. You emit the molecule, it doesn't know to which reaction site it should go. Once you declare a reaction site that consumes some molecule, that binds, as we say, the molecule to the reaction site. And then reaction sites are immutable, so you cannot modify the chemistry once you have defined it. This is a very important feature of the chemical machine. It makes chemistry statically defined and immutable, which makes reasoning much easier. So let us now look at the first example where I will count. So there is this counter molecule again, and then I will get a blocking molecule that will return a reply when the counter reaches the value 0. This is the test code. Let us examine how that code works. So we define the molecule emitter C with integer value. We define molecule emitter Declarative with unit value. Then we also define molecule finished with unit value. And then the get, which is a blocking molecule with unit value and string reply value. You see, we are free to define any number of molecules we need and call them by any name that we like. So this is the abstract chemistry. We can define now chemical laws with these molecules. So here's how we define them. Let me interchange the order. Now the order of reactions is completely arbitrary. It doesn't matter what the order is. The first reaction says that the molecule C, carrying value X, reacts with molecule Decker, carrying a unit value, if the X is positive. So that if the value X is positive, then the reaction starts. Otherwise, it doesn't start. Now, since reactions are arbitrary Scala, we can use all features of the partial function here. We can have arbitrary pattern matching, arbitrary guard conditions on the case expression, and to the right of the case expression we can have arbitrary Scala code. There are no restrictions. On the left hand side we can have any number of molecules. We can have repeated molecules, like for example C of X plus C of Y plus C of Z, whatever we want, as long as this is valid partial function in Scala. But I digress. So the first reaction says that when the counter carries a value that's positive, then you can decrement it. The second reaction says when the counter carries a zero value, then the finished molecule is emitted and the counter molecule is consumed. It's not emitted back. Now, note that this reaction has a single input molecule. But this reaction will only start when there is a molecule C in the soup that carries the value 0. So then the molecule finished will be emitted. And then this third reaction says the molecule finished reacts with the molecule get and sends the reply. Now the molecule get is the blocking molecule, so the syntax requires two pattern variables, one being of unit type and the other being of the reply type. Let's look at the types here. You see, reply has a type reply emitter with types unit and string. Finished has a type M of unit, so this capital M is a molecule, non-blocking molecule. Get has a type blocking mol value here, and here it has the type B. So capital B is a type for blocking molecule emitters. So this is not quite the same, as you can see, that this is this implicit reply emitter that you did not define. We did not define it in the code. It is already included in the definition of a blocking molecule. And then there is some code that emits the initial value of the counter. Let's say it's 10,000. Then we go from 1 to 10,000 and emit 10,000 decrement molecules. And then we call the get. So this get is a blocking call which will reply with done only when there is a finished molecule in the soup. The finished molecule in the soup is there only when there is a C of 0, and the C of 0 is only there after 10,000 decrement molecules have been consumed and 10,000 instances of this reaction have been run. Now, since there's only one C that we emit, one copy of C, these reactions cannot run 10,000 of them in parallel. Each one consumes this single C, and so only one of these reactions can run. While the reaction runs, the C is consumed. It's not present in the soup, so another reaction cannot start. And then at the end of the first reaction, let's say, the C will be emitted back, and then the second reaction can start. So because we have only emitted one copy or one instance of the molecule C, into the soup, we have effectively made all this chemistry single-threaded. Although this is actually run on a multi-core machine, and it could have used many threads. Let us run this test. So we expect the test to pass, and we'll see how much time it took. All right, let's run it with 100,000. All right, so another important thing that I'm going to talk about is that you can implement reactions in local scopes. This is the next test. In this test, it is very important that the molecule C should be emitted only once into the soup. What if the application code by mistake emits several copies of molecule C? Then this entire logic will break down. The Decre molecule could react with any instance, any copy of C, so the chemical machine might pick several different pairs of C-Decre to react at once, and so the decrement will not be applied to the same C every time. In order to prevent this from happening, we can define all these molecules in a local scope of a function. The function makeCounter will return a tuple of Decre and get. Now note that the function does not return C, so it returns two molecule emitters, Decre and the get. So here you see the types that it returns. These are the types of the molecule emitters. But it does not return C. It emits C into the soup, but the code that calls this function cannot emit any more C. The code does not have access to the emitter C. It's hidden, encapsulated in the local scope of this function. In this way, we can make it safe for application code to use chemistry library code, so to speak. So the make counter could be part of a library. It returns you the molecule emitters, the new molecule emitters it defined, and it's safe to use them. You know that the counter has been initialized to the value n, and then you can decrement and get. You cannot break this chemistry by inadvertently emitting an extra copy of C, because it's not in your scope. So this test runs just the same as the previous one. It's the same logic, except that the counter is defined in local scope. So this is what I illustrated just now. Note that local scopes are not part of the chemical machine paradigm. This is part of our programming language. So we can take a functional programming language, Scala, and we can add joint calculus or chemical machine features on top of it, and we can benefit from both. The chemical machine is orthogonal to the programming language. It can be embedded into any programming language. I have previously implemented the chemical machine in Objective-C on the iOS platform and in Java on the Android platform. it's just as easy to implement as in Scala, except for the syntax. Of course, the Scala syntax is much more readable than the syntax of those other languages. But I was able to use all the features of those languages together with joint calculus. So in this example, we use the chemical machine together with Scala in order to guarantee encapsulation and safety. Scala also guarantees that these values are immutable. So in this way, we can use all features of Scala. We can use the type system, for example. You see this type is a molecule emitter for a molecule that carries a value of type molecule emitter. It's completely fine and type safe to do things like this. A molecule emitter in this example, which is not what I was showing in the test code, the molecule get takes a molecule emitter as a value, and then it emits that molecule in the reaction body. So that is a slightly more advanced way of getting results out of reactions. That is, you give an emitter to a reaction, and the reaction body will call that emitter. So the reaction is defined. You don't know what emitter will be given to the reaction because that's the value on top of the molecule. So you can do that kind of thing, type safe and functional. So in my view, the chemical machine is very much suitable into being embedded into functional programming languages. There are lots of positive synergy that comes from that. Many examples can be seen. If you look at the main repository of the Chymyst, the test code contains many examples. For example, dining philosophers, game of life, parallel OR. There are all kinds of, these are unit specs. I have even a toy implementation of the Paxos algorithm. There are some unit tests, but also just some demos and algorithms like barriers, rendezvous, and so on implemented in these tests. Here's an example of how to implement the future primitive. So what does future mean? It means a function that will be executed in the future. So that's very easy. You just have this function get, and you can get the value back. Asynchronous execution is immediately available in the chemical machine, so there's no need to have a special future primitive. You can get values. You can do MapReduce. So let's look at MapReduce. Suppose we have a number of values. We want to perform some function in parallel on all of these values, and then we want to collect results. So the map step consists of, let's say, multiplying number by 2, and the reduce step consists of putting all the results into a list. How do we implement that in the chemical machine? We need to ask the first question: what are the molecules that are necessary to implement this? Well, molecules obviously needs to be one molecule instance for each of the data items that you need to process. So let's say each of these, so this is your initial array, let's say each of these numbers will be carried by molecule C, so the carrier of this. In order to implement the map step, we need to put the result on some molecule. So let's say that would be D. So clearly, we just need a reaction that takes C and produces D. And once we write this reaction and we emit many molecules C, then all these reactions will run in parallel automatically. Okay, so the result will be that let's say here we emit several molecules C. After all these reactions run, and they run automatically in parallel, we will get a bunch of molecules D. Now, how do we actually gather the results? Now, we need another reaction that will gather the results, and the result must be carried on a molecule. What would that molecule be? Let's call it res for result. That molecule needs to carry a list of values. And then the reaction will be that this molecule reacts with a D molecule and puts the value from D onto the list. Finally, we might want a get molecule that will get the value from the list like we do before. Well, this is a very simple example, not very realistic, but let's look at my test code. I believe it's here, MapReduce. So here I actually have more realistic code because I check the size of the list. So the get molecule actually will not react with the result molecule unless the list is full, unless everything is done, and this res will accumulate all the resulting data. So this is this condition. And that code actually works. So I emit D for, well, I call this D and R. Well, the values, you see, you can easily rename that. Call this C. Sure, the IntelliJ will refactor that if I want. Let's run this. So, all right. So basically, that's how it works. Note that the result is non-deterministic in the order of the results here. And that's okay in most applications. You don't want to specify exactly the order in which things run in parallel, as long as the final result is correct. So in this way, we can implement a MapReduce. My repository is full of examples of all kinds of concurrency problems, and I encourage you to look at the tutorial which explains how all these examples are designed. So I have a large tutorial which is going to be a book. Here is the table of contents of the book. And the main goal of this tutorial is to explain how you reason about concurrency in this paradigm. So you start with the problem setting. So for example, here is a chapter on readers, writers. And then incrementally you figure out what molecules you need, what reactions you need, and you write your program. Now programs are usually very short, and once you learn how to reason about molecules, you will find it very easy and visual. It's much easier to reason about data or objects that are present than to reason about processes that are running in unknown order with unknown state, especially when that state changes with time. Here's an example of implementing dining philosophers. We introduce molecules T1 to T5 representing the 5 philosophers that are thinking, and molecules H1 to H5 representing the 5 philosophers that are hungry, and also molecules F that represent the forks. So for example, F12 is the fork between the philosopher 1 and 2, and so on. And then we write reactions. These reactions mean that the first thinking philosopher starts to think for some time, and then it becomes hungry. And the hungry philosopher reacts with 2 forks, so it takes 2 forks, starts eating for some time, and then releases the thinking molecule, emits the thinking molecule, which means that it models the state of the philosopher that is thinking, and also emits the 2 forks back to the soup. So as I explained, the chemical machine works by first consuming all these input molecules for a reaction to start. So they are all consumed atomically, which means that, let's say if we have F12 that these 2 philosophers want, only one of them will be able to start. Only one of these 2 reactions will be able to start. The chemical machine will not deterministically choose which one will start, but it's guaranteed that only one of these will start, because we are not going to emit more than 1 copy of each fork into the soup. So that will automatically exclude the possibility that 2 of these reactions, like for example, the first and the second one, start at the same time. So that is what we want. Note that this code is completely declarative. We basically translated the problem formulation from the English to chemical reactions. Now, if you look at the test code for this, this is the entire code of a runnable application. So I define functions random wait, eat, and think. And I define all these molecules, and then I define this code. I emit initial molecules. This syntax is just convenience. It's the same as doing this. It's exactly the same. This plus is just a chemical notation, which is done for cosmetic convenience. So if I run this, you see, this is the entire code. There's the entire solution of dining philosophers. Very obvious what it is doing, and it's obviously correct. That is what it means to be declarative. You just translate the formulation of the problem from your specification into executable code 1-to-1, and it is correct. I can run this. And I will see messages printed as each philosopher starts eating or thinking. So let me stop this. Let me go back to comparing the actor model and joint calculus, or the chemical machine. Imagine that we wanted to evolve the actor model by imposing new requirements. So here we impose 3 new requirements. The first requirement is that the chemical actor, so to speak, should be automatically started whenever messages arrive. So the user code should not have to allocate or start or create actors explicitly or manipulate actor references explicitly. The user code only sends messages, and something is done automatically correctly. The second requirement is that the chemical actors should be able to wait for a set of different messages, consuming them atomically. The third requirement is that messages should carry statically typed values. Now, if you logically examine what follows from these requirements, then you find that the user code should not declare actor instances, but it should still declare computations that need to be done on each message. So the user code declares these computations in some way. Also, messages must be labeled to indicate which computations consume them. Also, automatically created actor instances must be stateless. Since they're created automatically, there's no need for or no possibility for them to have persistent state. Each actor instance is created and then destroyed. It's created, this so-called chemical actor, as I temporarily call them now, it's created just to process a message, and once it's done, it's deallocated, destroyed. So it must be stateless. And message emitters are not specific to actor instances, they're specific to these labels or to data, which makes them easier to reason about as well. So here's a comparison. In the a.k.a, you would create an actor reference and another actor reference, and then you would send a message to A, or you send a message to B, then you send another message to B, and so on. So you would explicitly create a new actor and then explicitly send a message to that actor. Whereas in the chemical machine, so these computations go here, but the computations are not references to actors or to specific processes that run them. These are just declarative definitions of what computations are available to be run. So when you say go, nothing is created or run. You just specify what computations need to be done in the future. And then you emit the data items on the molecules, which is quite similar to sending messages here to actors. But the labels A and B are not specific to a particular computation, or rather, they're not specific to a particular instance of the computation. They're specific to what computations will be consuming these messages, but not to instances of computations. So these computations will be automatically instantiated. And also note that B can be consumed by these two different computations, which is impossible here. So, and the computation needs to wait for two messages at once, which is impossible here. But these are consequences of our requirements. So the fact that message emitters or molecule emitters are specific to the kinds of data and not to the instances of computations, that makes things much easier to reason about. Remember the examples with MapReduce. The carrier molecule or the result molecule, these are things that we reason about as specific to the data. The result molecule carries the final data. The molecule C carries the initial data. The molecule D carries the intermediate data. We do not reason about processes that run. We reason about data that exists or that should be created. Also note that parallelization is automatic. We emit several instances of the molecule C, and then several instances of this computation are automatically run. We do not specify when to run them or that they should run in such and such parallelism. The parallelism is automatic. The blocking molecules are similar to the blocking send feature of the actor model. So if you need to block and wait until some reaction starts and sends you a result, you can do it using a blocking molecule. So reaction is analogous to an actor, although reaction is automatically started, whereas an actor in the actor model has to be created explicitly. Emitted molecule is analogous to a message sent to an actor, but actually a molecule is not sent to a specific instance of a computation. It is sent to the soup to be consumed as necessary or as possible. So if we compare how programming looks when we program with actors versus programming with reactions in the chemical machine, with actors, the user code must create and manage explicit actor instances, and actors will typically hold mutable state or change their behavior. Therefore, the programmer, or rather me, we have to reason about the data on messages and also about the running processes that will consume these messages. When we program with a chemical machine, processes automatically start. So all we need to reason about is what are the molecules that are present. Whenever the input molecules are available or present in the soup, the reactions will start. And many reactions will start at once, and that's safe because they will consume different instances of input molecules. So there is no shared state and there is no race condition on the shared data. Let me also show you a more advanced example of chemical programming, which is to implement the parallel merge sort algorithm. The merge sort algorithm is implemented in the chemical machine using a chain reaction, so to speak. That is, a reaction that defines other reactions and starts them, and these reactions in turn define and start further reactions, creating a tree of computation in this case, or a chain reaction. Here's how it is implemented as pseudocode at high level. As always in the chemical machine, all the data must be on a molecule. So the initial array that needs to be sorted must be on a molecule. So let's call this molecule merge sort. Now this molecule will react with itself, or rather by itself. It does not require any other input molecules except itself. So by itself, this molecule will start a reaction, which will split the array into two parts. Then it will define this new reaction, which will merge the results. So sorted 1 and sorted 2 are new molecules that it will define and emit. And the sorted result is an emitter that it received from an upper level call. So this is the recursion. So it emits low-level molecules recursively. Let's look at the actual Chymyst code. We define the merge sort molecule as a molecule carrying a tuple of an array and an emitter carrying an array. So this emitter will be the sorted result, and this was the initial array. So when this reaction finishes, the sorted result emitter will be called with the result. So this is like continuation passing, if you're familiar with that. This is the continuation, which will be called when the result is finished. So this is where it's called. The reaction immediately returns, calls the result continuation when the array has length 1. Otherwise, it defines two new emitters defines a new reaction that will merge the two halves of the array. So these are the sorted results now, and so it calls the emitter for merge sort, giving the sorted result emitters as the second argument. So here's how it would work. Initially, you would emit one merge sort molecule with the initial array and some emitter as the second argument. First, this molecule will create a sorted 1, sorted 2, will split the array into part 1 and part 2, and then it will emit itself with part 1, sorted 1, and also another copy of itself with part 2 and sorted 2. Each of these will again cause the same reaction to happen, each time defining new sorted 1 and sorted 2 molecules with a new reaction, because this definition is inside the scope of the reaction, which is a function scope. Each time you call a function, you define a new reaction site and a new emitter, or rather two new emitters. These emitters are distinct from all other emitters defined by different instances of this reaction. So there is going to be no confusion. They're going to be reacting only with each other. At the end, the sorted molecules will be emitted. They will react. Sorted result will be emitted, which will be sorted molecule at the previous level, and so on. Finally, when everything is done, the sorted result is going to be emitted with the final result. So this is the code. So the final result is this emitter that I'm going to use. So the code is call merge sort with initial array and the final result emitter, which is this emitter I define, and I define a reaction for that emitter. So you see, this is the client code. It defines a reaction for this emitter in any way that we wish. In this case, it's just a simple reaction that fetches the result and makes a blocking call with that. But it can be anything, any other reaction. The merge sort does not know what reactions are defined for this emitter. It just calls that emitter once here and once here. So that's the entire code of the merge sort algorithm. The entire parallelization and scheduling and figuring out which part goes with which part is all here. It's all in this code. It's very short, and I have tests that verify that this algorithm works correctly. So let me run this now. It just runs the merge sort on a small array. Right. There's one feature that I would like to talk about that I recently implemented in Chymyst, which is not usually present in the joint calculus presentations or descriptions. And this feature is what I call pipelined molecules, or ordered message channels. Let's talk a little about how Chymyst works under the hood. The reaction scheduler first examines all the present molecule instances in the soup in order to find what is the next reaction that could be scheduled. So when the reaction scheduler does this, usually it needs to look at many molecule instances. So for example, you have 10 molecules A and 5 molecules C and so on. and there's a reaction that says A of x plus C of y when x greater than 0 and y greater than x, and so on. Then the reaction starts. In order to schedule such a reaction, the reaction scheduler needs to find the molecules whose values satisfy the conditions. For that, the reaction scheduler usually needs to examine all or many molecule instances until it finds some molecule instances that satisfy the conditions, or the reaction scheduler determines that there are no such instances and so no reaction can run. But in some cases, it is sufficient for the reaction scheduler to examine only one molecule instance of C, for example. So this could be so for one molecule or not so for another molecule. It depends on the specific chemical program that is defined, and for each molecule could be different. If this is true for a specific molecule, then it is sufficient for the reaction scheduler to hold all the instances of the molecule in a linear queue or a pipeline and take the first one from the queue to examine what value that has, and if the value fits the condition, you can use it and start a reaction, and if it does not, then it is not necessary to look at any other instances further down in the queue. That is the definition of pipelined molecule. If the chemical program is such that it is sufficient to look at only one molecule instance and still be able to schedule all the possible reactions, then this molecule is pipelined. And Chymyst has code that automatically selects pipelined molecules. So certain molecules become pipelined. So that is the /p that we have seen in the tests over here. So this is the /p. It tells me that the counter molecule is pipelined. The decrement molecule is also pipelined. So this is an automatic optimization that Chymyst does. What is the condition for pipelining? So here I will explain only how this condition is formulated. To understand this, we need to consider the condition for starting a reaction as a predicate, as a function that returns true or false, the Boolean function. This function depends on values x, y, z. For instance, if we have a reaction with A and B reacting and conditions for x and y, then this could be this predicate. Reaction can start with molecule A of x and molecule B of y if we have a molecule B of y in the soup, and if x is equal to 0, and if y is greater than x. That could be code that looks like this. Let me continue my ammonite here. So I'll show you an example how this could work. So for instance, A is a molecule carrying an integer value. B is a molecule carrying an integer value. And then R is a reaction that says A of x plus B of y if x equals 0 and y greater than x. And then we get, let's say, B of x plus y. It doesn't matter right now, just an example. So in this example, we just say cite R. So you see R is this reaction which takes A plus B and does something. Now let's emit A of 3. Let's emit B of 5. So now you see no reaction can start because the condition is that x must be 0 and we did not emit a of 0. So let's say log soup, and you'll see a of 3 and b of 5 are present, and there is no /p. So Chymyst has determined that in this case the molecules A and B cannot be pipelined. If I emit a of 0, do log soup, then there's a of 3. So a of 0 has been consumed, and we again have b of 5. Well, in this case it's a little strange to look at this, but it's just consumed, but this is just an example. So in this example, the molecules A and B cannot be pipelined. Consider the predicate. Now, the condition is that this predicate must be factorizable into a conjunction of two other predicates, P and Q. So if this is so, if there exist predicates P and Q such that this is a Boolean identity, then the molecule A can be factorized. So A is the molecule whose value is X. So then it is pipeline. Otherwise, it's not pipeline. So if this predicate is factorized into P of X and Q of Y and so on, then all of these molecules with values X, Y, and so on will be pipelined. So in this case, obviously, this predicate cannot be factorized because it has a condition that couples together the values of Y and X. So this is not a conjunction of some condition on X and some condition on other things. So similarly, we can see it's not factorizable with respect to Y. So Chymyst performs this computation automatically, tries to factorize the predicate. This is static analysis, so this is done before your program runs. And I have a formal proof using Boolean algebra that this is an optimization that preserves the chemical machine semantics, but I will not present that proof right now. So to conclude, the chemical machine has this notion of molecule, notion of emitter, notion of blocking emitter, reaction, emitting a molecule, and reaction site. Now, in academic joint calculus, the same things are called by different names, which I actually found more confusing, such as message on channel, or channel name, or process, or joint definition. I found those names confusing. I don't like this terminology, but if you read academic papers on joint calculus, that's the terminology they use. I use terminology of the chemical metaphor, and this is the code that corresponds in Chymyst to these notions. So the Wikipedia page is actually quite confusing if you look at what it says about joint calculus. I cannot really understand what that all means. Like, for example, communication occurs only on defined names. That is confusing. What does it mean? Why could it occur on undefined names? Just some jargon that only maybe some academics understand and no software engineer really knows about. And so don't look at the Wikipedia page. Read the tutorial that I showed you, and it's hopefully much more understandable. There are other implementations, just to give you a perspective of the chemical machine or joint calculus I could find. So one of these, namely JOCaml, is actively maintained. Others are not. JOCaml is a compiler fork of OCaml, so it's a dialect of OCaml, which is completely compatible with the OCaml platform, so it's easy to install, and you can play with it or implement applications in it today. This is the only usable version of joint calculus other than the Chymyst that I'm developing that you can download and use today. How is my implementation different from previous ones? Well, I have a little more convenient syntax. I have more checks on code. So for example, if I have a reaction that says, for example, a of x goes to a of x plus 1. Oops, I forgot the case. So that reaction, if I do side R now, then we see there's molecule cannot be bound. It's already bound. Let's define another molecule, say CC. Let's define a reaction. I don't see an error here. Let's see if this works in a test. So you see, what I'm trying to do here is I'm trying to create a live log situation where a molecule causes a reaction that runs forever and produces more and more molecules of the same kind. And I expect an error here. Oh yeah, that's an error. So that's a compile time error that says unconditional live log. Input molecules must not be a subset of output molecules. So it detects at compile time that here this reaction is useless. You started with some molecule and it immediately produces the same molecule again, which will immediately cause the same reaction to be repeated. So this is an infinite loop. It will be completely useless in any application. And so this is a compile time error. This does not work in Ammonite right now. I think because of the way Ammonite processes macros in its interactive REPL, but it does work in ordinary Scala C compiled code. So I have a number of checks like this where you detect live log or give warnings about possible live log if it is not unconditional. I have some fault tolerance. When a reaction throws an exception, the exception is caught and there's an option to retry. I have thread pool control, so I can specify that certain reactions should run on certain thread pools. I can specify the thread priority or the number of threads in those thread pools, which is useful for certain applications when you want to control which reactions should be highly available with low latency, maybe, and other reactions do not need to be low latency, so you put them on different thread pools. I have some monitoring and unit testing APIs that go beyond the log soup that I demonstrated and allow you to run meaningful unit tests on your chemistry, such as after this molecule is emitted, that molecule needs to be emitted, or something like that. So to conclude, the chemical machine that I described is a declarative and purely functional concurrency paradigm. It is similar to the actor model, but it is easier to use, and I would describe this as more purely functional. than actors. It does not have state, does not have shared state. It is strongly typed, and the code in the reactions can be seen as pure functions from the initial molecules to the final molecules. Code in the chemical machine is short, often declarative. You can implement different concurrency primitives or concurrency situations in a very visual manner. So I'm developing this new implementation of the chemical machine called Chymyst, which is a full-featured implementation of joint calculus with no restrictions on the code or conditions you can have in the reaction. This implementation has some static code analysis which prevents errors before you run your program. It has some industry strength features. I'm still working on more conveniences and better features, but right now it already has thread control, pipelining, which is useful in many situations, and automatic optimization. It has fault tolerance, unit testing, and debugging. I have extensive documentation which is being worked on, but already is a couple of 100 pages long. In the future, I will work on maybe thread fusion, such as if reactions can be run on the same thread so we don't switch the threads, or try to implement macros for continuation passing transformation so that blocking molecules are converted to non-blocking molecules automatically, which can be done in a number of cases, so that performance is improved. And some more advanced features are being worked out, such as back pressure and distributed cluster runtime. The entire example code for this talk you can see in this repository, and the slides for this talk are available also on GitHub. That concludes my talk.